Welcome to the deep dive. Today, we are really getting into the nuts and bolts of building software, specifically looking at creational design patterns in C Sharp. If you're coding in C Sharp and you feel like you type the word new about a million times a day, or every time you add a feature, you're touching like 20 different files, well, this deep dive is aimed squarely at you. Our mission is figuring out how to create objects without veining ourselves into a corner.
Yeah, it's fundamentally about making things flexible. Creational patterns and the Gang of Four, the GoF, really laid the groundwork here. They're all about separating how an object gets made from the code that actually uses it. It's about decoupling.
Exactly. Now, just a heads up on what we're covering. The classic Go list has abstract factory, but based on how things are often done in C Sharp today, we're making a slight adjustment. Abstract factory's job making families of objects that often falls to dependency injection frameworks now.
That's a fair point. It reflects modern practice.
So we'll hit the four core GoFef creational patterns: factory method, singleton, builder, and prototype. And then for our fifth, we're bringing in dependency injection, or DI, because frankly, you can't talk about modern decoupling without it.
Agreed. Those five give you a really powerful toolkit for managing object creation effectively in C Sharp.
Okay, let's kick off with the factory method. And maybe the best way to grasp it is to remember the problem it solves, right? The pain point.
Definitely. Imagine you have some client code, maybe a method, and inside it, you've got this logic. If the input says car, then new car. If it says motorcycle, then new motorcycle.
Standard stuff seems simple enough at first.
But it breaks a key principle. The open-closed principle, the OCP. That principle says your code should be open for adding new stuff, but closed for changing existing stuff. With that if-else block, if you want to add, say, a bus.
You have to go back into that original method and add another else if. You're modifying existing working code. Risk increases.
Precisely. That's tight coupling, and it violates OCP.
So the first step people often take is the simple factory idea, just pushing that if-else logic into a dedicated factory class.
Yeah, that's a common idiom. It centralizes the creation logic, which is better. The client asks the factory for a vehicle, and the factory figures out which new to call. It hides the decision.
But the real Go factory method pattern takes it further, doesn't it? It uses polymorphism.
Exactly. This is where it gets more sophisticated, but also more powerful. Instead of just one factory class handling everything, you create parallel hierarchies. You have your products, maybe an iVehicle interface, with car and motorcycle implementing it.
Okay, the product side.
And then you have a factory hierarchy. An abstract vehicle factory class defines that there's a method for creating a vehicle, like create vehicle, but it doesn't implement it. Or maybe it has some common logic.
It defers the actual newing up part.
Right. The concrete factory subclasses, like sports vehicle factory or economy vehicle factory, they're the ones that actually implement create vehicle and say new sports car or new economy car.
So the client code just talks to the abstract vehicle factory. It doesn't even know about the concrete factories.
Mostly, yes. Or it gets the specific factory it needs somehow, maybe through configuration. But the point is, the client calls the same method on the factory, regardless of which concrete factory it's using. And if you need to add a luxury vehicle factory,
You just create the new factory class and the new luxury car product. You don't touch the client code. You don't touch the existing factories. OCP is happy.
that's the elegance of it. It preserves that open-closed principle beautifully.
All right, so if factory method helps manage creating different types of objects, singleton is the opposite in a way. It's about ensuring you only ever get one instance of a specific type.
Exactly. One instance, and usually a single global way to access it. It's probably the most well-known pattern,
Yeah.
and maybe the most controversial.
Yeah, let's talk about the why first. When do you actually need only one instance?
Typically, it's for things that are inherently unique or expensive to create or need central control. Think about a system-wide configuration manager, a logging service that writes to one file, maybe a hardware interface where there's only one physical device. You don't want multiple objects fighting over it.
Makes sense. But then there's the controversy. I remember reading that Eric Gamma, one of the original Go authors, basically said later he wished they hadn't included it or that its use is often a design smell. That's pretty strong.
It is strong, and it's because singletons can introduce hidden dependencies in global state, which makes code harder to test and reason about. They can be misused quite easily.
So why cover it if it's potentially problematic?
Because sometimes that single instance constraint is real, imposed by the system you're working with. And also because developers do try to implement it, and frankly, they often mess it up, especially with multiple threads.
Right, the threading issue, the
Well,
naive C# way, just if instance new singleton, that breaks instantly if two threads hit it at the same time, doesn't it?
instantly.
Yeah.
You get two instances. So historically, people used lock statements around the check and creation. That works, it's thread safe.
Yeah.
But lock introduces contention. Every thread trying to get the instance, even after it's created, has to potentially wait for that lock. It can become a bottleneck.
Okay, so what's the modern C# sort of best practice?
The recommended approach now is using lazy-T. It's built into .NET. You wrap your singleton type in lazy singleton.
And lazy-T handles the tricky parts.
It does. It guarantees thread safety using highly optimized internal mechanisms, much better than manual locking, usually. And crucially, it provides true lazy initialization. The instance is only created the very first time someone accesses the value property of the lazy-T object.
So it's safe, efficient, and only creates the object when absolutely needed.
Exactly. So the takeaway is, if you find yourself absolutely needing a singleton, and you should question that need hard use lazy-T, and always ask if dependency injection could maybe manage that single instance for you in a cleaner way.
Okay, moving on. Let's talk builder. If factory method is like ordering off a menu, one choice, one result, builder feels more like, well, building something complex piece by piece.
That's a good analogy. Builder is for when creating an object isn't a single step, but a sequence of steps, and the final object can have many different configurations. Think about constructing a complex object where you might have, say, 10 optional parameters in the constructor. That gets messy fast.
Like building a car, you need an engine, wheels, body, seats, lots of parts, maybe different kinds of each.
Precisely. The builder pattern formally breaks this down into roles. You've got the product, the final car object. You have the abstract builder interface, which defines methods for adding each part. Set engine, add wheels, paint body.
Then concrete builders implement those steps, like electric car builder or truck builder.
Right. They know how to build their specific kind of car, part by part. And then there's the director.
The director. What's its job?
The director knows the sequence of steps needed. It takes a builder instance and tells it what to do in order. Okay, builder, first set the chassis, then add the engine, then the wheels. It orchestrates the process.
Okay. But isn't that just shifting the complexity? Instead of one complex constructor, now I have like 4 different classes or interfaces to manage?
That's a very fair question. The complexity is only worth it under certain conditions. First, if you need the same construction process, the director's logic, to create very different representations of the product. Use the same director with an electric car builder, you get an electric car. Swap in a diesel truck builder, the same director steps now produce a diesel truck.
So the director's reusable across different builders.
Exactly. And second, it's really useful when the object being built should be immutable once it's finished. The builder accumulates all the parts, validates them perhaps, and only gives you the final complete product at the very end via a getResult method.
And in C#, there's that fluent interface approach too, right? Method chaining.
Yes, that's a very popular and elegant variation. Instead of a separate director class, the builder methods, set engine, add wheels, each return the builder instance itself.
So the client code can chain the calls together.
Right. The client effectively becomes the director, defining the sequence in a really readable way, like builder.setengine.addwheels.paintbody.car. It's fluid, clear, and very common in C#.
Okay, so builder for multi-step configurable construction, often leading to immutable objects, potentially using that fluent style. Got it.
Now for something completely different, the prototype pattern, this one isn't about building from scratch at all. It's about creating new objects by cloning an existing one.
Cloning, like treated role plus C, curricle plus V for objects.
Kinda, yeah. You have an existing object, the prototype, and when you need a new object like it, you just ask the prototype to make a copy of itself.
Why would you do that instead of just using new or a factory?
The main reason is usually performance or resource cost. If creating the initial object was really expensive, maybe it involved complex calculations, database calls, loading huge amounts of data, you don't want to pay that cost every single time you need a similar object. Cloning an existing instance can be much, much faster.
Okay, speed. Makes sense. But cloning in C#, that brings up the whole shallow versus deep copy issue, doesn't it? This feels like the technical core here.
It absolutely is. C# provides a built-in method, memberwise clone, which is protected, so you usually expose it via a public clone method. But memberwise clone performs a shallow copy.
Shallow copy, remind me.
It copies value types like integers, booleans directly, bit by bit, that's fine. But for reference types, other objects nested inside your prototype, like say an engine object within your car prototype, it only copies the reference, the memory address.
So the original object and the cloned object end up pointing to the exact same engine instance of memory.
Precisely. Which means if you change something on the engine through the clone, it also changes on the original prototype's engine because they're sharing it. Usually that's not what you want.
Right, that sounds dangerous or at least unexpected. So you often need a deep copy.
Most of the time, yes. If you want the clone to be truly independent, you need a deep copy. And C# doesn't give you that automatically. You have to implement it yourself.
Wow.
Typically, you'd start with memberwise clone to get the shallow copy done easily, but then you manually go through each reference type field in your object and create a new instance of that nested object, copying its values over. You might even need to call clone recursively if those nested objects also contain references.
So using the prototype pattern forces you to really think about object relationships and whether you need shared state or complete independence, field by field.
Exactly. It pushes memory management and object graph concerns right to the forefront. It's powerful for performance, but you have to be deliberate about how deep the copy needs to go.
Okay, we've reached our fifth pattern, dependency injection. And we flagged this earlier. It's not technically one of the original GoF creational patterns, but it's so fundamental to modern C# and achieving decoupling, which is the goal of creational patterns.
Absolutely. DI is really a technique to achieve a broader principle called inversion of control, or IOC.
Yeah.
It fundamentally changes how objects get their dependencies.
So let's contrast it. The old way, maybe? A driver class needs a car. So inside the driver's constructor, it just goes this dot my car, new car. Tightly coupled.
Very tightly coupled. The driver knows how to create a car. It depends directly on the concrete car class. With DI, that's inverted.
How so?
The driver class becomes passive. It simply declares, I need something that behaves like a vehicle, usually by requiring an iVehicle interface in its constructor or through a property. It doesn't create the vehicle itself.
So who does create it?
Something external. Often, in modern C#, this is a DI container, like the one built into ASP.NET Core, or libraries like AutoFac or Lamar. You configure this container at the start of your application, telling it, when someone asks for an iVehicle, give them an instance of car.
And the container handles creating the car and passing it into the driver when the driver is created.
Exactly. The responsibility, the control over object creation and wiring is inverted. It moves from the component driver to the external container.
Okay, and we talked about different ways to actually get that dependency into the driver. What were those injection techniques again?
There are a few common ones. The most prevalent, especially for required dependencies, is constructor injection. The dependencies are simply parameters on the constructor. Public driver, iVehicle, vehicle. The driver can't even be created without a vehicle.
Makes sense. Ensures the object is always valid.
Yeah.
What else?
Setter injection, sometimes called property injection. You have a public property, like public iVehicle, vehicle get it set. The dependency is set after the object is created. This is good for optional dependencies or things that might need to change during the object's lifetime. You can mark properties required in recent C# versions to make them mandatory even with setter injection.
More flexible, maybe?
Can be. Then there's method injection. The dependency is passed directly into a specific method that needs it, like public void perform maintenance, iTool, tool. Useful if the dependency is only needed for that one operation.
Transient need. Okay. And the last one, interface injection.
Interface injection is a bit more architectural. The class needing the dependency, driver, implements a specific interface, like iDependency consumer vehicle, which has a method like inject iVehicle. The container then finds classes implementing this interface and calls the inject method. It's less common now with modern containers, but it's another way to signal and fulfill dependencies.
Gotcha. And just to be crystal clear, DI is the technique of passing dependencies in, while DIP, the dependency inversion principle, is the solid principle that says high-level code shouldn't depend on low-level details, but both should depend on abstractions.
Perfectly put. DI is how we achieve DIP in practice. It's the mechanism that makes that principle work in code. #tag outro.
Wow, okay. We've covered a lot of ground. Factor method for polymorphic creation, Singleton for that unique instance, used with care. builder for complex step-by-step assembly, prototype for cloning existing objects, and finally, dependency injection for fundamentally decoupling our components through inversion of control.
It's quite a tour, and it really highlights that thinking about how objects are created is crucial for building systems that are easy to change and maintain.
We also touched on that categorization thing as DI creational. Architecture.
Yeah, and honestly, the label isn't the most important part. Understanding what it does, enabling loose coupling, enabling IOC, that's key. But if you had to pin it down, its main role is architectural, structuring the application. But it definitely works hand in glove with how and when objects get created, so it lives right alongside these creational concepts.
The big takeaway seems to be, don't just sprinkle new everywhere without thinking. Abstracting instantiation pays off massively in the long run.
Absolutely. And theory is one thing, but you really internalize these patterns by, well, by using them. You have to code them up, write a factory, struggle with getting a Singleton thread safe with lazy T, figure out if you need a shallow or deep copy for your prototype.
It reminds me of that story about Euclid, right?
Right.
When the king asked for an easier way to learn geometry, Euclid supposedly said, there's no royal road to geometry.
Exactly. There's no royal road to clean C# design either. You got to get your hands dirty, experiment, see what works for your specific problem.
So the challenge to you listening is, pick one of these patterns you're less familiar with and try implementing it this week. Refactor some code, see how it feels.
And keep asking questions. If you reach for a Singleton, stop and ask. Could DI do this better? If you're building a complex object, is a builder really necessary? Or is a factory or even a simple constructor enough? Be critical.
Excellent final thought. Thanks for breaking all that down.
Well, my pleasure. It's fundamental stuff.
Indeed. Well, that's our deep dive for today. Until next time, happy coding.